Guys, we are starting our next lesson. Name of the lesson is Rotation and Revolution. Right. The syllabus includes rotation and few things about rotation, and then few things about revolution also. Let's begin. When we stand on our earth and look outside, we feel like this. We are standing stationary at a place, and all other celestial bodies, including stars, sun, moon, are all moving. But you know the reality that Earth is located at the center of the solar system, and all other planets are moving around it. It's not only the solar system and planets; the entire Milky Way itself is circling around the center. Not only the Milky Way, the entire universe itself is moving. Okay, that's in those part. All those things are not important. Now, let's begin with the movements of Earth. Mainly, there are two types of movements. One is rotation and revolution. Rotation is the movement of the Earth, or the spinning of the Earth on its axis from west to east, and Earth takes 24 hours for making one whole rotation. Earth has to cover 360 degrees, and for that, Earth takes 24 hours time, and this causes day and night. Revolution, on the other hand, is the motion of the Earth around the Sun in its orbit. And the orbit of the Earth is not circular, it is elliptical in shape. And to cover this whole distance, Earth takes around 365.25 days. That is 365 days and approximately 6 hours time. So these are the two moments of Earth. Now, rotation causes day and night. When one side is experiencing day, the other side is experiencing night. And not only that, because of the rotation of the Earth on an inclined axis, we have different places experiencing different duration of day and night. So the length of the day and night differs from place to place and time to time because of the rotation of the Earth on an inclined axis. Here you can see an animation of the rotation. When this side is receiving daylight, the other side is receiving or having night time. And in between you can see a line which acts as a boundary between the day and night. This line which acts as a boundary between day and night is called as the line of illumination. It's not a line actually, it is circular in shape, it goes all around the Earth, right? And this demarcating boundary between day and night is called as circle of illumination. Now the period of rotation, if you ask the exact period of rotation, it is 23 hours 56 minutes and 4.09 seconds, and this is what is called as a sidereal day, right? But for our convenience, for calculation purpose and all, we round it and we take the period of rotation or the time taken for the rotation as 24 hours, or 24 hours is taken as a normal calendar day. Now the effects of the speed of rotation, right? Before we see what are the effects, we have to understand what is the speed of the rotation of the Earth. The speed of the rotation of the Earth is 1670 kilometers per hour at equator. That means the speed is not same everywhere. At the equator the speed is maximum and it is 1670 kilometer, and as we go from equator to polar region, the speed decreases. The thing is that at the equator Earth has to cover this much distance, that is around 40,000 kilometers, but the time is 24 hours. But if we go towards the north or south, say for example at this latitude where you can see 1550 kilometers, so at this latitude again the time taken for rotation is same 24 hours, but the distance has reduced. If you go further north again, distance is less, time is same, therefore the speed is comparatively less. So from the equator to pole, the speed of the rotation of the Earth decreases, and at the equator is the maximum speed, and it is about 1670 kilometers. Okay, so that speed is almost double the speed of an average speed of Air India flight. Right, moving on, the effects of speed of rotation. The three main effects which are created by the speed of the rotation of the Earth are the Coriolis Force, the deflection of the cyclones and anticyclones. Sorry, it's not cyclone, it's anticyclone. Then the bulging of the air at the equator and the flattening of the air at the poles. These are the three main effects of the speed of the rotation of the Earth. Keep in mind, it is the effect of speed of rotation, not the effect of rotation, it is the effect of the speed of rotation. First one is Coriolis force. It is a force generated by the high speed rotation of the earth. This force causes deflection of freely moving objects like air, that is wind, and ocean current. And because of this force, air or the wind deflects towards right side in the northern hemisphere and towards left side in the southern hemisphere. Right, this is a small demo here. In the northern hemisphere, you can see this wind is going towards the north, but due to Coriolis force, it is taking a deflection towards the right side. In the southern hemisphere, same thing, but there the deflection is towards the left side. So this force is generated due to the high speed rotation of the earth. Now the second thing is the deflection of cyclones and anticyclones. Again, typing error, it should be anticyclone. So here you can see the cyclone is not moving in a straight line. This is about the Fani cyclone. It affected or it was originated in the Bay of Bengal last year. And see, you can see the path. It is not going towards, sorry, it's not going straight. Instead, it is going towards the right side. So this kind of deflection is also due to the Coriolis force. You can see this shows the size of a cyclone. This is the currently active cyclone, the Umpun cyclone. It's about to reach the West Bengal coast by tomorrow. So you can see the cyclone is covering the entire Bay of Bengal and even parts of eastern India. Right? Such huge phenomena are also deflected due to Coriolis force. That is another important. That's another important effect of the speed of rotation. And when it comes to the rotation of the effect of the rotation, mainly there are two effects. The first one we discussed was the effect of the speed of rotation. This is the effect of the rotation. Other one is the effect of speed of rotation. This one is the effect of rotation. So here mainly two effects. One is day and night. Other one is variation in temperature. Rotation causes day and night. When there is earth rotating, one side experiences daytime, the area which receives light, and the other side experiences nighttime. And corresponding to this one, whichever the side is receiving daylight, that area will have more heat, and the other side will have comparatively low temperature. These are the two effects of rotation of the earth. In addition to this, rotation of the earth creates two forces. One is Coriolis force and other one is centrifugal force. We have already seen what Coriolis force is. Then there is another term, Coriolis effect. Both are almost same with a slight difference. Coriolis effect, the term was first used in the year 1835 by a French scientist named Gustave Coriolis, and according to him, this force, that is the Coriolis force, causes Coriolis effect. Now what is Coriolis effect? Coriolis effect is nothing but the same thing which we saw, that the due to the Coriolis force, freely moving objects, say for example wind, deflects towards the right side in northern hemisphere and deflects towards the left side in southern hemisphere. Right. So the force that causes the deflection is Coriolis force, and this one particular effect, that is deflecting towards the right side and left side in north and southern hemisphere, is called as Coriolis effect, and it is given as a law is called Ferrel's law. So according to Ferrel's law, due to Coriolis force, wind deflects towards right in northern hemisphere and left in southern hemisphere. Right. So the law which suggests this deflection is called as Ferrel's law, and the effect is Coriolis force, Coriolis effect, and the force behind this is called as Coriolis force. Now, Coriolis effect is absent at the equator. Right, wind will not deflect towards any direction at the equator, but as we go from equator to pole, the Coriolis effect increases. The reason is the speed of the rotation decreases. We have already seen that speed of rotation decreases from equator to pole. Right? Because of this, Coriolis force increases towards the polar region. And here there's a depiction of the same thing again. You can see this one example. Say for example, the dark line shows the actual path the wind is supposed to follow, but due to Coriolis force, it is deflecting towards the right side in northern hemisphere. Here also same. If the wind is coming from the north, it is supposed to come to the side, south, right, directly there, but due to the Coriolis force, it is getting deflected towards the right side. When it is in the southern hemisphere, same thing, but the wind deflects towards the left side. So this force that causes the deflection of the wind is called as Coriolis force, and this deflection, this effect is called as Coriolis effect, and the law suggesting this effect is called as Ferrel's law. Or in simple, you can keep it like this: due to Coriolis effect, objects are deflected towards the right in the northern hemisphere and deflected towards the left in the southern hemisphere. Now the second force which is generated due to the rotation of the earth is centrifugal force. Just like any object which is rotating, there is always a force which is directed away from the center of the axis towards the outer side, right? A force which is directed away, this force is called as centrifugal force. And here you can see a student spinning a hammer, say for example. So from the axis of his rotation, there is a force which is actually pushing this outward. So this force is called as centrifugal force. Same thing is there on earth also. When the earth rotates at a very high speed, there is a force which is directed away from the equator, right? But we are not thrown outside because we are all held together by another force, that is gravity. Since the gravity and centrifugal force is balanced, we don't have any issue on earth. So the force that is directed away from the center of the earth, from the axis of the earth to outward, is called as the centrifugal force. Now it causes the bulging of equator, right? Because of the speed of the rotation we have because of the rotation of the earth we have centrifugal force, and due to centrifugal force the earth's equatorial region is slightly bulged outward and the polar region is slightly flattened. That is why the shape of the earth is not exactly spherical, and this shape is called as the oblate spheroid shape. Now another important thing is the centrifugal force balances the centripetal force. There is another force which is again generated due to the rotation, the movement of the earth. So the centrifugal forces balances the centripetal force. Now the topics that we covered so far are very simple, but just to revise it one more time: rotation, definition and all, then the speed of rotation, period of rotation, then effect of speed of rotation, then effect of rotation, then Coriolis force, Ferrel's law, and the centrifugal force. Moving on, we have the next topic: revolution. Revolution is the motion of the earth along its elliptical orbit around the sun. The movement of the earth around the sun in an elliptical orbit, and it takes approximately 365 days and 6 hours, or 365.25 days for making one complete revolution, right? And this is the orbit. You can see it's not an exact circle. In some places it is very close to the earth, and in another place it is little far away from the sun, right? So this shape of the orbit is called as elliptical shape, right? So the period of revolution, or the time required for the earth to complete one round around the sun, that is our year, is exactly 365.25 days, or 365 1/4 days. So this time is called as a sidereal year. But there's a problem: we cannot use this sidereal year every time. If you see a calendar, we have only 365 days. We don't have 365.25 days. So if we go for taking the sidereal year, or 365.25 for calculation, it will make a lot of confusion. So here, in order to avoid this, what we do is, from 4 sidereal years, right, that is 360.25, we take all these 0.25, that is 1/4. That means it will form 1 day, and this 1 day is added to the 4th year. Every time 1 day is additionally given to the 4th year, and that year is called as leap year. And whenever there is leap year on that year, in the calendar you can see 29 days will be there in February. 2020 is a leap year, 2016 was leap year, 2012 was leap year, and now the next leap year will be in 2024. 2020, 21, 22, sorry, 21, 22, 23 will have only 28 days in February, but in 2024 again there will be 29 days. That is, these 6 hours, additional 6 hours are taken together to form 1 day, and it is added to the next year's calendar, right? That is leap year. This is how we are adjusting with the time in case of calculation. Now another term which is related to this one is the perihelion and apogee. These two terms actually indicates two positions of the earth. The mean distance from sun to earth is approximately 150 million kilometers. The mean distance, the average distance from sun to earth is approximately 150 million kilometers. Why the mean? Because we already know that the shape of the Earth's orbit is not exactly circular, it is elliptical. That at one point of time, Earth will be close to the Sun and the other side will be the farthest from the Sun. Right. Now here, when the Earth is nearest to the Sun, that position is called as perihelion. Right. That is at present, sorry, that is 147 million kilometers. And the farthest point from Sun to Earth is called as aphelion. Right. In Latin, helion means sun, up it means away, peri means near. Right. Now it is easy to understand. You can take the first letter. Right. Aphelion, that is A stands for away. Right. So the other one is perihelion. Easy to understand. Right. So there are two terms, perihelion and aphelion. Perihelion means the nearest point of Sun to Earth, and the other one, the farthest point from Sun to Earth, is called as aphelion. Now, usually perihelion happens on 3rd Jan, right, and the aphelion on 6th January, 6th July. Now, the next topic is the speed of revolution. The length of the orbit of Earth is approximately 940 million kilometers. It's not 940 kilometers, it is 940 million kilometers. And Earth has to travel the entire 940 million kilometers in 365.25 days. So if we divide this distance by this many days, the speed will be somewhere like this. The speed of the revolution of Earth is 1,07,000 kilometers, right? And it is comparatively faster than anything that we have on Earth. When we short it down, it is around 30 kilometers within a second. By the time you read 30 kilometers or 29.7 kilometers per second, Earth would have covered another 30 kilometers. So that is the speed of the revolution of the Earth, right? So when the Earth moves around the Sun at this speed, it takes 365.25 days for the Earth to cover one whole revolution. And if we compare this with the speed of some of the fastest thing in Earth, like fastest car is only 430 km per hour. It's nowhere near this one. Or if you take the fastest aeroplane in the world, that is the North American X-15 aeroplane, the speed, the maximum speed it can achieve is only 7,200 km. Or if we go for the fastest unmanned plane, again it's only 11,000 km per hour, right? But the speed of the revolution of Earth is more than a lakh 7,000 km per hour. So this is about the speed of the revolution. Now the coming topics are related to revolution only. All these in the coming videos. Thank you.